Hi, everyone. Thank you for joining us today. My name is Yasmina Greco with O'Reilly Media, and I will be your host for today's webcast. Today, folks, we are thrilled to have Tony Parisi live in our O'Reilly Media studios to present to you all WebGL Up and Running. Tony is the author of the new O'Reilly book, WebGL Up and Running, Building 3D Graphics for the Web. I will turn the program over to Tony in just a moment, but first I'd like to go over some housekeeping things to help you get the most out of today's webcast. You'll want to open the group chat window if you haven't already done so. This is where we can interact with each other during the event and where you can submit your questions for Tony. We find that our audience usually has a lot of good knowledge to share, so we encourage you all to chat freely during the event. However, if you have questions for Tony, please preface them with a capital letter Q so we know that they're for him and we can make sure he sees it for Q&A. You can also open, move, and resize any of the other widgets. If you would like to tweet from the Twitter widget today, you'll need to give it permission to access your account. Our hashtag today is WebGL, all one word, and the Twitter widget will automatically append it to your tweets so you don't have to. If you have any problems during the event, please take a look at the Help widget. If you continue to have problems, please post it in the chat room and one of our staff will help you right away. For choppy audio or stalled visuals, please try refreshing your window. And remember, the best thing you can do for a good audio stream is to close out any apps that could be interfering. People always ask, so we'd like you to know, we are recording today's webcast, and we'll have an archive ready usually within 48 hours. And folks, at this time, it is my pleasure to turn the program over to Tony for his presentation. Hello, Tony.
Hi, Yaz. How you doing?
Great.
Hi, everybody. Today we're talking about WebGL and how you can get up and running quickly to build 3D into your web applications. First, a little bit about me. I'm a serial entrepreneur. I've worked in technology startups for years. I specialize in 3D graphics. I created the original standard, co-created VRML with my friend Mark Pesci several years ago now. It was a little bit early to bring 3D into a web browser. We didn't have broadband. We didn't have fast hardware like we do today, but we learned a lot, and we actually have been able to use some of those learnings to feed into the development of WebGL, which I'm talking to you about today. I'm also, as Yaz mentioned, a book author. I've written WebGL Up and Running. O'Reilly's the publisher. And in fact, Yaz later will tell you about some deal we're running today so that you can get a discount on the book. And so with that, let's get rolling. WebGL is the new 3D API standard. It's OpenGL ES running in your web browser. OpenGL ES stands for Embedded Systems. That means a small footprint of OpenGL graphics that can run in a phone, a little device, a tablet, or in fact in your web browser. So OpenGL ES was around first, and over the last few years has been adapted to become WebGL. That API is wrapped in JavaScript, so you can write JavaScript code just like you build your other web applications and talk directly to the 3D hardware on your machine through your web browser. It's supported in nearly all of the modern web browsers, Internet Explorer being an awful exception. We can talk about that more later during Q&A if folks want to. But it's running really well in Chrome, really well in Firefox, Opera, and Safari. It's running on a lot of devices now. If you go into a consumer electronics store like Best Buy and buy one of those Chromebooks for $400 and something, it actually runs built-in on that. It runs on tablets, runs in lots of phones, Android phones. Not complete coverage, but quite broad. It's been shipped in the desktop browser since 2011, so it's maturing quite quickly, and it's quite awesome. Let's have a look. So I know you folks in screen share land probably aren't going to get the same frame rate I'm getting, which is 30 brilliant frames a second at least of this live jellyfish forest, which is being displayed now. These are the Chrysaora species of jellyfish, And this was actually developed by a fellow named Alexander Ruddick when he was an intern at Google last summer. He now works at LucasArts with developing games. And if we see here, I can drag around. Again, you're not going to get the frame rate, but you'll see it update eventually. And so I'm interacting with this jellyfish for us. I can move everything around and get beautiful points of view. I can see the light streaming from the top. If I click up on the top bar here, I can load a debug console that lets me look at all the different bits and pieces that go into this beautiful WebGL presentation. And one thing to note about that user interface I'm interacting with before I start clicking is that was all built in HTML. We're going to come back to this topic a little bit later in the webcast, but the point is that you don't need to have a custom game toolkit to develop your user interfaces on top of WebGL. You can just use HTML, HTML5, all the stuff you've come to know and love in terms of developing UI widgets just sit right on top or beside of your WebGL. So let's take a quick look here. I'm just going to play around with this debug console and change different parameters of this presentation. I'm now simply looking at what's called a diffuse color. The entire shape of the geometry of each jellyfish is being painted with a single color. Each one of these little things I'm going to click on gets eventually blended together to give you the ultimate picture we were looking at. Now if I click the color radio button, what we're seeing is a texture map or a bitmap applied to the entire surface of the jellyfish. So if you looked at this, it's probably just a JPEG file, and that's just getting wrapped around in interesting ways on the polygons that represent that jellyfish. I can also look at what's called normals. This defines how shading impacts the jellyfish. So the blue and red areas define other 3D vectors that determine the shape and shading of these animals. I can also look at this purely in wireframe. What this is doing is showing all the 3D vertices that make up the shape of the jellyfish. That data, along with all the other color and normal data that I've shown you so far, ultimately gets built up together, blended together into pixels that represent the surface of the jellyfish in this composite view I'm showing you now. So we're going to talk more about shaders in a little bit because that is actually a significant topic in WebGL. Finally, I can play with a few other bits and pieces here. The skybox is an infinitely far away background. I've just removed that so you can just see the jellies. I can also turn on a grid. This is an XYZ grid rendered with line rendering, so you can kind of get a sense of the coordinate system these 3D jellyfish are swimming around in. All right, let's turn that back off. Get our skybox on and take one more view of this beautiful presentation. So, how does that all work? Here's how it works. WebGL is actually a drawing API. It's similar to the 2D Canvas API you may be familiar with. You get a region of your window to draw graphics into. In this case, it's not 2D graphics, it's 3D graphics. And you draw the 3D graphics by obtaining a special context. We're going to look at code in a minute for doing that rendering. And then you use a series of very low-level drawing calls, and you're going to see what those look like in a minute, to actually get your bits on the screen. It's worth pointing out there's no file format standard that goes along with this. There's nothing like an HTML or even an SVG or, say, VRML, the thing I worked on years ago, to actually feed content directly into the browser. That is up to the application writer. You would create your own files or export your own files out of authoring tools and then read them into whatever libraries you're using. There's no real object model. Again, it's not like SVG. It's not like a DOM. So you're just doing drawing, and you're drawing repeatedly if you have animations, every animation frame. We'll get into that a little later. So let's just take a quick look at a sample here. I'm going to bring up about the most trivial example we can think of, which is the simplest thing you can really draw, which is a white square in a window. That looks pretty simple, but what it turns out when you're using low-level WebGL, and this is the only example today that we're going to go into that uses low-level WebGL, you actually have to do a lot of hard work to get that square on the screen. I don't have a line counter here, so I'm going to reopen this in Eclipse. I want to see what the line counts look like because it's a bit staggering. You will see that this file, which is just there to draw that square, is about 180 lines of code. Now, don't freak out. We're not going to do it this way for most of today's session. But I just wanted you guys to see what the underpinnings, the drivetrain underneath WebGL is, if you will, before we get into how we're really going to do this in practice. So the first thing we're going to do is actually try and initialize our WebGL. I'm selecting some text now in my Eclipse. And so this body of code, this little helper function I wrote called the init WebGL, we're going to pass that a canvas object. The canvas object was created, subsequently I'll show you in the file, but it's basically a canvas just like an HTML5. Again, we're going to get a special drawing context here. What we're going to do is try to get a WebGL drawing context. You will note here the canvas.getContext call. You can say experimental-WebGL in there. These days, since WebGL is no longer experimental, I believe most browsers, at least Chrome I know, supports just passing in the string WebGL into that call. So if you're successful, you're going to get back a drawing context called GL, which this function will return. If you're not successful, that means either your browser doesn't support WebGL, or it does, but your hardware doesn't support it, which for most modern computers isn't going to be a problem, but it may happen. There are some hardware cards that just don't work with WebGL. But assuming you're successful and good to go, the GL object is returned and then used by the application. Then what we go do is basically tell GL, this is how big a viewport, how big of a rectangle all the drawing is going to take place in, and we're setting that to the width and height of the canvas element. So if you know how to do canvas programming, or if you know your DOM elements and your DOM calls, all this stuff should be familiar to you. You don't really need to know 3D graphics. You'll learn a little scary stuff in the next 2 minutes with me, but beyond that, I think you'll be able to track it if you've done any 2D drawing before and just extrapolate into a third dimension. Okay, here's one other special thing we're going to do that is 3D that you'd never see anywhere else, and that's initializing some matrices. Matrices are big buckets of numbers used all the time in 3D mathematics. We don't have time to get into what they really do today, but we need a couple of them in order to actually draw our things on the screen. We need to create a matrix that will transform our vector drawing calls in 3D into what we call a world space, and then we need another thing, another matrix, to transform them then into screen space. So we create these two matrices, and what's interesting about both of these is that they're using a brand new data type built into web browsers that was actually originated from WebGL, which is called a float32 array. They're called typed arrays in your web browser, and they're buckets of floating point numbers, buckets of integers that are tightly packed. They're not your typical JavaScript array, which is really just a hash table of a bunch of generic values. And so that's pretty different and very important for performance in the WebGL world. So you create these packed arrays, fill them up full of numbers, and that's what this little function's doing for us. And the specific values in these numbers are a little bit obscure, so I don't want to get into them now. The point of this is it takes a square that you would think of in your mind when you're drawing squares in a drawing API and turns it into a square that will appear the right way on the screen. So let's leave it at that. The next thing we do is we create the geometry for the square. We're going to use a WebGL-specific object called a buffer, which is just a bucket of data. That's going to contain 3D vertex data, which is specified here in the variable verts. So we create that. These are basically just the corners of a square. You'll notice the zeros at the end of each of those entries. Those are the z values. This is a square. It's not a cube. It's not some other extruded object. It's simply a flat square. So the z coordinate is always 0. We set that buffer data into the pipeline of OpenGL, WebGL, and that's all we need to do. And then we return an object to tell our application that it's going to use this particular bucket of data to actually render. Okay, the last little bit of the setup we have to do is create something called a shader. Everything in WebGL goes through a shader program. Again, don't be freaked out. Don't be scared. Once we do this initial setup and look at this example, you're going to start using a toolkit after this that creates shaders for you. You just give it a few parameters, and it knows what to do. A shader is responsible for drawing every pixel you see on the screen through WebGL. First, it takes vertices, those 3D coordinates, and transforms them in a way that they can get onto the screen in that viewport that we looked at. Then there's something called a fragment shader that operates on those vertices to actually color them. It can take the colors, the pixel values from a bitmap. Remember I called those things texture maps earlier. It can create color values you feed into parameters. It can use any old variable you set in. You could do time-based things and actually update colors based on time if you're animating. It's a program. It's written in a little C-like programming language we're about to get to right here. So here's the source for that vertex shader and fragment shader. These are just JavaScript strings, and I've basically created them by appending a bunch of text with new lines. These are going to get fed into a shader compiler, that is run by the WebGL pipeline. So that's what my next little function is here, init shader. It takes all of that stuff above, assembles them by creating two shaders, a fragment shader, vertex shader, creating a new program, and attaching these bits and pieces together through a process called linking. This is all just mechanical framework setup stuff that you have to do in GL that if you're fortunate, you'll have a toolkit to help you with, and we're going to have a toolkit real soon. So with all that preamble out of the way, here is actually the code to draw the square. We're going to clear the background. So we're going to have a nice black background. That's the GL clear color call, which it sets it as a value. And then we're going to actually call gl.clear to do it. Then we're going to set up that vertex buffer that we talked about earlier. That was the buffer full of data that represented those square coordinates. Then we're going to use the shader program. And then we're going to feed it the parameters it needs, those matrices I was talking about, because the shader needs to use those to actually put the bits on the screen. So there it is. We set that all up. We call that in our onload function, which is just done, out of the body of an HTML. We'll see that at the bottom if I scroll down a little more. You'll see how onload is triggered in a typical fashion. In this first example, I didn't want to get jQuery and all the other stuff in there, but for the rest of my book examples and the examples we're going to show in the webcast today, I'm using jQuery and its ready function, a little more reliable than using the old school onload. Just trying to keep this simple and keep the line count to under 200 lines. But as we can see, 180 lines of code to draw a square, that's pretty exhausting. So thankfully, we're not going to do it that way in the real world, and we're going to talk about that in a minute. But there it is. That's your first program in WebGL done the hard way. So back to the PowerPoint. Now let's say you're a web developer who wants to build an online game. Well, again, the first thing you're going to do is start looking for a framework, because you're probably not going to build all your code that way. And unless you're a game engine developer by vocation or by experience, you're probably not going to want to invest the time into building your own application framework and engine on top of WebGL, which is super powerful but super low level. So the first thing you probably want to do is choose a framework. We're going to talk about that in a second. And then we're going to cover a bunch of topics that are required to build a game. We're going to build a simple level of this racing game you see a screenshot of here. So we're going to talk about how we draw graphics, get graphics on the screen. We're going to talk about how we load 3D models out of programs, because you're not going to hand code all your models. You're probably going to get them out of some modeling package like 3D Studio Max, Maya, Blender, SketchUp. So we're going to talk about that. You're going to want to animate bits and pieces, because this is not a static rendering, so you're going to want to animate parts of your game, and we're going to talk about how you do that. Likely your user is going to interact with the game in some meaningful way. In this case, in a racing game, we're just going to use the keyboard to drive around. In other games or 3D applications, you're going to want to use the mouse. We'll briefly talk about how that works with WebGL. We're going to show how to create some special effects. We're going to bring that wonderful 2D and 3D integration capability to bear to build a nice heads-up display for the racing game, plus some pop-up screens when you're done with your game level. We're going to talk about how you bring sound together with this stuff, because, graphics is one thing, but a game needs sound. Most 3D applications will probably need other media, sound and video. So very important to talk about that. And then a few techniques about how to make your web page robust. WebGL doesn't work everywhere yet, so we'll talk about WebGL detection in a little more detail. It's possible you got WebGL running, but then your graphics card, actually winds up on you, locks up on you or something. There's ways to detect that in your web browser and get an event. We're going to talk about that. And finally, we'll put all those pieces together and show you a working game level. So let's get to that. So how do we choose a framework for building a game? Well, if you Google out there in WebGL right now, you'll actually see a lot of links, and there's a lot of stuff out there. I've got experience with some of them, so I thought I'd share a few thoughts on that. And these are a smattering of frameworks and libraries that I know about. There's something called Three.js, which we're going to use in all our examples today. It's an open source library. Actually, all of these are. There's a couple others called CubicVR, SceneGL, and GLGE. These are libraries. They're not really game engines. What they do is they give you higher level 3D objects to do your rendering and interaction with, so you don't have to do all of that WebGL coding yourself. But they don't give you any game engine features such as behaviors, collision, physics, AI, and all the things that go into building a game. So those are separate topics, and we're starting to see some engines emerge on top of these other frameworks, or sometimes with their own rendering underneath. Mozilla has a project called Gladius that's built on CubicVR. There's a product called Kick.js. I just recently saw something called Ninja Power that a lab in Motorola is building and putting out on GitHub. I'm writing an engine called the Skybox engine. You can find that up on GitHub. Or you might want to roll your own, but most likely when you want to get up and running, you don't start there. So we're going to pick one and run with it for the rest of this talk. I chose Three.js. It's great. I like it a lot. It's very well maintained by a pretty vital community of open source programmers. The main programmer is named Ricardo Cabello. I forgot your last name. His nickname is Mr. Doob, and he's a really wonderful guy living in Barcelona. He's the main author. He's got a couple of other core collaborators. It's a great open source project on GitHub, and you see the URL there. It's high performance, really efficient. It's got a lot of features to get you going. It's extensible, so you can add your own features if you need to. And it really is kind of best practices 3D graphics if you know any 3D graphics and know the kind of objects you're used to dealing with, a polygon mesh, a texture map, a material, a light. They have some animation capability in there. So all of those things sitting on top of WebGL just make it a really great choice. And as a little sidebar, I'd like to say that the fact that you can even build an engine like this on top of low-level WebGL and build a whole engine in JavaScript is a testament to how fast the JavaScript runtime engines now are in Chrome and Firefox and the other browsers, that you can actually build a game engine or a rendering engine in JavaScript and have the performance you need. So this is pretty fantastic. And so, yeah, I highly recommend you give Three.js a try. Oh, and one other interesting thing is if you do need to fall back to 2D, you can write Three.js code that will render to a 2D canvas as well. In fact, somebody wrote a plug-in renderer for Three.js using ASCII. I've seen a spinning cube that was drawn in ASCII characters with all plus signs and zeros. It's pretty funny. So, yeah, great toolkit. Highly recommend it. We can go look at that square again and how that would be done instead of with all those lines of WebGL. We can do it in Three.js. Now, boom, same thing. You can see visually it's just the square again, but now we're going to look at that code in Three.js. Now we'll see that instead of 180 lines of code, including all the bric-a-brac that comes with your HTML, it's 42 lines of code, and only about 25 plus of those are anything to do with Three.js. So it's now all in our onload function. I didn't need any helper functions. I get my div element to render into. And the first thing I do is I create a 3.WebGL renderer object. The 3 package is a minified compiled package using Google Closure. So Three.js, all the source files for Three.js, if you explore all the sources, you can see them when you get them off GitHub. There's a build process that builds that into a compact one file that you can include. So you include the Three.js source in one line in your HTML. Probably have that in here. Right here. So I've got a snapshot of my subdirectory of my project called libs. There we go. So we create a 3.WebGL renderer. That's an object that will render into the viewport using WebGL. I set its size to be the entire size of my container div using the offset width and offset height properties. I then add that as a child of that DOM element, and boom, my WebGL renderer is ready to go. It still doesn't have any content, though. So I'm going to create a scene, a Three.js scene, which is the master object, if you will, the root of a tree of objects. This is a hierarchical system where I can add children, and they will render and be placed with the other children. The other thing I need to do is I need to create a camera. You cannot see anything in WebGL without a camera. Imagine a 3D coordinate space with objects in it. You need to place your eye point in such a way that that is where everything is drawn from, and that's what the user, the viewer, is looking at. So what I've done here is I've created a perspective camera, which is the typical kind of camera. It does a 3D perspective rendering with a 45-degree field of view, kind of a typical default. It's a little bit of a narrow angle, if you can picture that. And then I basically give it how big of an aspect ratio I'm going to use, which is the width divided by the height. And then I give it some front and back clipping information. That says don't render anything closer than 1 unit to me and farther away than 4,000 units. These are parameters you can play with as you learn to get around your WebGL application work. I set the camera back 3 1/3 units. I add that camera to the scene. Now all I need to do is put some geometry in it so that I can see it. So I'm going to create a plane. It's a built-in Three.js object that's a 2D plane. Now, it's 1 unit by 1 unit big. I'm going to create a mesh object. That's the actual drawn object that uses that geometry. And I'm going to tell it what the surface properties are. Remember, I had to write a shader to do this last time. I don't have to write the shader. Three.js has written it for me. And I create a white material. By default, the basic material in Three.js, and a material is anything that gives me those visual properties, the color, the texture map, any bumpiness, all that. I'm going to create a basic material that's just flat white. Attach that to the geometry to make this new mesh, and that mesh object gets added to the scene. Once that's done, all I need to do is render it, and that renders the square. So now in 23 lines of Three.js code versus 150 plus in raw WebGL, we've got the same result. So there we go. So now we know how to actually render a WebGL scene without, essentially killing ourselves and spending all day doing it. So with that in mind, we want to talk about one more preliminary topic, and then we're going to get on to building our game. So Three.js is great, but it's just a library. It doesn't give you any runtime support. It kind of makes you go through the same setup steps again. So even though it took that 150-line program and turned it into 30 lines, we can do better by taking the same repetitive Three.js tasks and putting them in a little application framework. I wrote one of these for my book that we're talking about today. I call it Sim.js. There's the link to GitHub on the page here. You can go get that separated. Also, a snapshot of that comes with in the WebGL book project that you're going to get the URL to at the end of the presentation. But basically, it wraps a lot of the common Three.js setup and tear down so that you don't have to do that, because that was a good part of what we just were setting up there. It implements something called a run loop. So the square we drew, we only had to draw once. But what if you're doing an animation? You essentially have to draw things repeatedly. And the way we do that is to use a helper called request animation frame. Request animation frame is something that's built into modern web browsers that you can think of as a replacement for set timeout. People used to do a lot of animations with set timeout, but the problem is the browser doesn't know whether you're using set timeout to do timers and alarms or whether you're using it to animate. So it can't optimize and it can't composite, essentially combine all of your rendered bits and pieces together optimally if you're using set timeout. However, if you're using request animation frame, the browser knows that when it calls your callback you've registered with that function, that you're doing drawing, and it will add it to the list of stuff that gets drawn before the next time it redraws. So we've got that support in Sim.js. We're adding mouse and keyboard DOM event handlers so you can just pick and use keys and get events back, because Three.js doesn't really do that for you. And then there's a few foundation objects in there that every application can inherit from. This is a really simple framework. I wouldn't necessarily recommend it for building an industrial strength app, but for your simple experimental work, for learning about Three.js and WebGL, for using the book that I wrote, great place to start, and maybe you can write something like that and make it better. I'd like to hear your feedback on that. So that was the last preliminary. Now let's get on to how we build the game. Before we look at specific bits and pieces of the game, I want to talk about one more topic in general, and then we're going to look at some code that supports this, and that's how you draw graphics using the Three.js library. So a lot of game development is about drawing graphics, and I couldn't think of a better example of showing you what's involved in drawing graphics than putting together a solar system, because it kind of has all the bits and pieces. So we're going to play around with a little toy solar system in a minute, and it's going to cover topics we care about a lot. Primitive shapes, cubes, cones, cylinders, spheres, squares, disks. Three.js has a lot of those built in. Polygon meshes, when a primitive shape isn't enough, when you want to do things like render Saturn's rings, and that's a donut, and there's no built-in shape for that in the Three.js library. Well, how do you do that? We're going to cover that. Rendering points and lines, very important in 3D graphics. So solar system is going to show us how to do that, because we've got orbit lines and stars for the points for the stars. The materials that go on the surface of these objects, those texture maps that represent the planets, the lighting model to shade them based on the location of the sun. We're going to talk about that. Textures, those are the bitmaps that go on the surfaces. We're going to cover that. Lighting, the way we actually realistically show where shading is in the scene. The transform hierarchy. So planets tend to live in a hierarchy. The planets revolve around the sun. The planets themselves have satellites like moons. We're going to show how those things work in a Three.js and WebGL setting. And then finally, we actually are going to write a shader. You know, I was dancing around that topic earlier because it's a little scary, but once you have an application framework such as Three.js and you want to do something really tricky and really custom, like get a sun swirling around, then you might want to write a shader because that's not easy to do without writing a little bit of code. So with that, let's actually go look at our solar system. So here you see the solar system. Again, frame rate, you're probably not getting the frame rate on the screen share that I'm getting, which is, I'm not seeing any jumps or jaggies or anything. I'm going to zoom in here, and that zooms very smoothly on my machine. What do we see at the center? We see a swirling sun. That was written with a shader. We're going to cover that one last. As we see planets coming around. All of these planets are in orbit. The orbits are relative to each other accurate. Of course, they're not really accurate. It would be sitting here a long time watching Jupiter go around the solar system, for example. But if you watch, you'll see that these are slowly moving. But you can see now Earth coming around, and Earth is spinning. It's actually rotating on its axis as it revolves around the sun. And the moon is actually revolving around Earth and has its own rotation that matches that of the Earth, as you know. And so we can see that, and thanks to the magic of the transform hierarchy, that Earth-Moon system could be placed where it needs to be in the solar system, and you can easily make a hierarchy of these objects without, any back-breaking sort of work, and we're going to look into that. And then you can see the shading over on the left of Jupiter here, on the back side of Saturn. That's using a lighting model. The textures, these are images that come from NASA, from jpl.gov. These are real satellite images. These are real space telescope images we're seeing of everything. So, we're getting the real stuff and then wrapped onto spheres that we built. Of course, most planets really aren't spheres. They are ellipses, but for our purposes, spheres look good enough. And finally, we see Saturn, not finally, penultimately, we see Saturn's rings here, and that's some custom geometry. We'll cover that. And then finally, you see the stuff that you really wouldn't see in the real world when you were looking out in space, the orbit lines representing where these orbital paths go. That's just line drawing, a primitive in WebGL and Three.js. We're going to cover that, and the points that go along to make the star background. So let's take a quick tour of the code. Back to my Eclipse. So again, these are all examples from my book, so that's what this chapter organization is all about. We're going to start by looking at the HTML file that brings all this together. I've got my preliminaries where I bring the libraries in, my sim framework, and then the classes that make up the solar system. There's a base planet class, which is the generic planet, not Earth, not Saturn. The other planets used to just put a sphere with a texture out in orbit somewhere. We've got our Earth object that has a really nice Earth implemented with shaders if you get close enough, and terrain and all this other stuff. We've got Saturn with the custom rings. We've got the sun, which is using a shader to do that swirling fireball. We've got the stars in the background and the orbit lines being drawn. And then finally a solar system object that's basically a composite object, an application that brings them all together. Now, interestingly, if you recall from the first example I showed, there was shader code written in JavaScript strings with the \n's and the string concatenation. I've taken a different tack here. The shaders that are going to be used for the sun, we're going to come back to these later, but while we're looking through the HTML file, I just wanted to show you. You can create script elements with essentially a custom script type so that the browser doesn't try and treat it as JavaScript. It'll just ignore it, but you can put all that content in a way that you can just format it in inline text in your HTML so you don't have to do all those string backflips. You could also put this in a separate file, .fs for fragment shader, let's say, .vs for vertex shader, and load them via AJAX. But that would have made life more complicated for me, and I'm lazy, so that's the way I did this. I did it with 2 embedded script tags. I got that technique from, I believe, Giles Thomas, the fellow who does the Learning WebGL site. Great site. You should go check it out. It's his blog. So anyway, all that stuff, script preamble, gets packaged up with your HTML file. In my document.ready, remember I'm using jQuery now, I get the container element. I create an application that's part of my sim.js app framework. It's a subclass of that I've called Solar System App. I initialize that with the container. That's going to do all the Three.js setup underneath. That's going to get me mouse handling. I was zooming in before. If you saw in the Solar System, that was a mouse wheel jQuery plugin. That stuff's all hidden in sim.js. So I initialize that, and then I call app.run. Under the covers, that's doing that request animation framework business, which I will show you right now. So if we look in libs, requestanimationFrame.js. That was written by Paul Irish. That is, there's a function that essentially wraps in a cross-browser way how to do request animation frame, which is, hey, if I'm running WebKit, I'm going to get it this way. If I'm running Firefox, I'm going to get it this way. If I'm running Opera, I'm going to get it this way. If I'm running Internet Explorer, I'm going to get it this way. One of those would have worked if you're in a browser that supports request animation frame. If you're not, then what we're going to do is fall back to set timeout because it still works. It's just not as optimized as request animation frame. All that stuff, thank you, Paul Irish. We put that in the Sim framework, and that's what's going to basically be the event pump for all of our animation and rendering. So now, let's go take a look at a planet. And we're going to talk about how to render primitives. That's the first subject we want to talk about. So if we look at planet.js, we see that that's a subclass of a sim object. The sim object is just a base object. We're going to create an orbit group. So you know how each planet's out in orbit some distance from the sun. So that's sitting in a group. A group is basically just a hierarchical element. You can think of it like a DOM element. The analogy is not quite exact, but it essentially lets you create a tree of children, and in that tree of children, the transformation information, its X and Y, Z positions, can all actually affect the descendant children's position. So that's basically a way of creating that Earth-Moon system and moving it out a certain distance from the sun. It's a way of creating a hierarchy of groups where one I'm rotating, another one I'm positioning, so I get all the orbits and all the revolutions and all the rotations in the right place easily. So I connect up a couple of these groups. I then actually create the globe for my planet, feeding it a texture map. Since this is a generic planet class, it could have been any one of those planets like Jupiter or Neptune. So I create it by creating a sphere primitive. This is a Three.js built-in. It's a unit sphere, and this tells me how finely I'm going to tessellate it. That means how many triangles I'm going to generate, 32 in the vertical and 32 in the horizontal direction. So that's a lot of triangles here. It's the square of that number. So about 1,000 triangles being generated per globe. So to have a really nice, fine-looking sphere. If I had fewer, it would look like a golf ball. You would see the bumps, so we didn't want to do that. So I've created a nice sphere. I load a texture map. That's a bitmap, and I actually create a new kind of material. It's called a Phong material. This is a graphics term. This will shade it. So if you saw there was that light source, let's go back to the demo real quick. If you see the light source around these planets, again, you can see how to the left of Jupiter, it's shaded because that's the side not facing the sun. It's darker, right? That's using this Phong material to do that. Again, we put our material together with a geometry to get a mesh, and boom, got a planet. We take that planet, we add it to the group. That's how we use primitives to draw. Next up, we want to draw those orbit lines. We do line drawing in Three.js. We create a bucket of geometry. We populate it with vertices. Those are 3D XYZ positions in space, basically tracing a circle. I didn't bother with doing an ellipse because the math's too hard for me and I'm lazy. So we just made a circle and put it out at that orbital distance, and then we created certain material type Three.js uses to render lines. We're saying it's a 2-width line width, half opaque, so it's not really cluttering up the display too much. So it's sort of semi-transparent, white line of thickness 2. I could be farther away or closer to that line. It'll always be 2 pixels thick. That's the way the shader draws it. And then I make a line object using that geometry material. Boom, I've got lines. Then I can make stars. Another primitive in Three.js and another WebGL rendering primitive is called point. It's a point. And what I do is I create geometry. Again, I populate it with vertices in a loop, and these are just random. I make groups of random stars. And then I play a really cheap cinematic trick, which is I put them so far away in a big donut around my solar system, so as you're flying through the solar system, you never really look like you're getting closer, so they look infinitely far away. It's a cheap trick to represent what's called the skybox. There are other ways to do it too, but this is to illustrate how you do point rendering in WebGL. Then we have our Earth, which I showed you already, but I'm going to show you one interesting part about it, which is the Earth and Moon put together. So that's an Earth-Moon system. Actually, I'm going to go into this version, earth.js. And what I do is, pardon me while I scroll, I create my globe for the Earth. I create a cloud layer, which is essentially just another sphere, slightly out. If you got close, you'd see the clouds. And then I create a moon. And that moon is just another satellite. And the trick here is I add it as a child to my Earth, and then wherever I put the Earth, and as it moves around in its orbit, the moon stays positioned relative to that. So it's always going to be rotating around that Earth no matter where the Earth goes. And you can see it now in its path as it moves around to the right of the sun on your screen. And that's how transform hierarchies work. The final bit of graphics to look at before we move off our solar system and get back to our game demo is that shader for the sun. Now, it is a little bit funky, and it may be beyond what most people are used to if you're a web programmer, and that's okay, because you don't have to get into this unless you're really, really ready to take on shaders. I would strongly suggest, if you haven't done stuff like this, let's say you haven't done pixel bender programming in Flash, which is a very similar thing, or CSS3 shaders, that you wait on building shaders yourself. Use Three.js. It's got a lot of built-in shaders to start. Look at the sample code. It's got 100 at least demos. It's great. But when you're ready and you want to be macho, here's what you do is you go in and you build a shader. In this case, I'll start with the vertex shader. Vertex shader is really simple. I'm going to output a value, and this thing is run on every vertex of that sun. So everything that's that sphere that shows up in that sphere we looked at for the sun's geometry is run through this pipeline, and this stuff is executed in the hardware in a special graphics language. I spit out the text coordinate, which is a texture coordinate. That's going to index into the bitmaps that are being used to shade the sun. There's a lava bitmap to give it that swirly fire look, and there's another bitmap with alpha channel to give it dark spots, sunspots. We'll go back and look in a second. Then these are kind of vanilla. Basically, these are canonical. These are what you do to map vertices from world space into screen space. That's done. Once that's done, we're going to go to where the real work's being done in the fragment shader. This takes two texture maps plus time and that texture coordinate as its input and basically just messes around with them. It's got a sort of pseudo-noise function it's pulling out. It's basically generating organic-looking noise by taking bits out of texture 1, and texture 1 is this basically alpha-shaded PNG. It's just got some noisy swirl, a pre-generated texture, which you can see in the samples in the images directory. I then pull out these texture coordinates, fiddle with them, and these are empirical numbers I put in the vec2 calls, basically just taking these vectors, multiplying by the time to animate, and that gives us a swirling effect. And this is all, I mean, seriously, it was empirical. I played with this stuff. I copied the original code from one of the Three.js samples. I'm no expert in Perlin noise generation and all these things, so I just learned as I did. The final result of this is a color value that's calculated by taking the original texture, which looks like lava, all that noise stuff, biasing a little bit by 2 just to make it brighter because I found that looked better, and I output that, and that's the final bitmap color that comes out, and the end result looks like this sun, which you can contemplate for a second here, which at 30 frames a second is swirling. On the webcast, I'm looking at it right now on the monitor, it's still swirling, so that's good. Hopefully you're seeing it the way I see it. So that's great, and that's all just done with math. How about that? But it looks pretty organic, so that's why we actually bothered to do shaders. So we're going to come back to shaders in another webcast, and we're going to move on to some practical game topics because we got about 15 minutes, and I want to leave time for Q&A. So real quick. So none of that stuff in that solar system was made by an artist. So apologies about that. You're looking at programmer art. Even Saturn's rings, I just did an equation to go trace what a donut would look like, a flat donut shape. But, you know, in the real world, in real 3D graphics and real games, you're probably going to get models out of a package like SketchUp, Blender, 3D Studio Max, Maya. And so what you're typically going to do is take those models and export them into some kind of format that WebGL can look at. Now remember, WebGL doesn't have a built-in format itself, so you've got to rely on the library that's being used. In this case, we're going to use Three.js's built-in support for a couple of different file formats. It has its own format in JSON, so pure JavaScript object-based format that it can read directly in and render. It also has a reader for the XML format called Collada, which is an open format that's output by a lot of tools. There's a converter that will command line in Python convert OBJ files, which is what I ended up doing. I got all my OBJ files for the game, and OBJ is a wavefront. It's an old-school wavefront format. It's been around forever. I got OBJ files from the game on a site called TurboSquid, which is a model-sharing site, turbosquid.com. You can get a lot of models for free. You can buy some for cheap, small dollars. Some go into the hundreds. Everything I used here was something that I could get for free, cobble together, and then get permission to use in the book and Webcast. So we're going to look at some of those. Now, the pipeline for making stuff in WebGL is still really primitive, guys. So just be aware you're going to be on the bleeding edge on some of this. The runtime is great. It's solid. But tools-wise, you may be out on the bleeding edge a wee bit. So what I did is I built a little model previewer, which I'm going to run through real quick. And one of the reasons I built the previewer is when you go get models off a place like TurboSquid or the Google 3D warehouse, you never know what you're going to get. You never know whether it was modeled at the origin. You don't know what units it's in. It might be in meters. It might be in inches. It might be in angstroms. It might be in some really obscure, coordinate space. So then when you bring it into your application, you may find that what looks like, a flower in a 3D modeling package ends up being the size of a skyscraper. So you might need to fiddle with it. So I made this little previewer and sort of empirically went in and fiddled with it. I found this Nissan model. I wrote a little code to figure out what the bounding box size was using some helpers from Three.js. And I come to find out that it is in these dimensions. Well, what are these dimensions? I had no idea until I went on Google and found the dimensions of a Nissan GTR car, and it turns out it's 182 inches long. So I found out these were in inches. So now I could take this into my game, which was modeled all in meters, and do a simple conversion, which I also looked up on Google because I'd forgotten because it's been a while. And I was able to convert that. So I used this little model preview to get these things in, figure out where they were modeled, if they were modeled even at the origin. You'll see when I bring in this Camaro, it looks great, but I'm looking at the back end of it. Its pivot point is around its nose. So when I bring this one into the game, I could have tried to, kind of adjust the model and bring it into another package, but I myself am not a 3D modeler, so it's easier for me to write a code, bring it into the game, and just transform it and offset it a little bit. So that's what I did. So I used this model previewer to do that. Let's go on to the next topic because I don't want to labor the code there because we're short on time now. But you can look at that model previewer when you get the book or the GitHub code for the book. Next up, let's talk about how we actually animate that scene. So animation is not built into WebGL either. That's something you do yourself in your JavaScript code. The Three.js library has some built-in support for animation. They've got a kind of keyframing system which moves animations from point to point over time and interpolates in between. I didn't like theirs, so I wrote my own in my Sim.js code, and that's what you'll see in this example. And we can build our own with JavaScript. And in fact, the solar system you saw was sort of animated, and I'll put that in air quotes. You can't see me air quoting, but those planets are moving around, but they're actually moving around based on a JavaScript function using time that just offsets things by a little bit every frame. If we were doing this right, we would actually model that on some functional time basis that used the actual elapsed time of the simulation. That's the right technique to do it. So that's the way I recommend you do it in your applications. The other thing about animation, and we saw that in the sun shader is essentially an animation. It's using the time value to make the pixels swirl. You can animate textures, materials, light, so you can make a moving spotlight to give a theatrical effect. You can make colors flash and blink to create a strobe. You can animate scale to make something shrink and grow. And all of that stuff can be done with keyframes or hand-coded, up to you. I built a little keyframe utility to make the car tumble when it crashes, and so I'm going to try and do that now. I tried screen sharing this earlier. Didn't work so great, but let's just see what mileage we get this time. Let me run a little what I call a gray box prototype for the racing game I built. All this does is it lets me keyboard control the car. I'm moving the car around, and you're probably not going to see enough of this. Yeah, here we go. You'll see the car as it's moving, hit the guardrails. It does a little sort of tumble animation bouncing off. And then when I crash into one of these boxed up cars, and it didn't, I think I just stopped. Hold on. Let me reload it. This time I'm going to make the car crash. If I can catch up to it, going as fast as I can. Just going to ram into the back of the purple car. You'll see a little bit of tumble. It jumped and then jumped back. So run this. Go get the code and run this one yourself, and you'll see these guys tumble. And you should go look at the keyframe animations that go along with that. Essentially, keyframes are just a list of points in time. Let's say over the course of 1 second, quarter second, half second, three-quarter second, whole second, and then keyframes, locations, positions, orientations that go with those time values. You specify a handful of those and let the runtime, the animation runtime, interpolate in between them using tweening functions. So it fills in, essentially, all the stuff in between. You'll notice also that when I was running that gray box prototype, I was driving the car was moving, I was using the keyboard to do that. So the great news about WebGL is it just uses your same things you're familiar with in a web browser to do mouse and keyboard interaction. You're just handling DOM events with your mouse. Now the trick with the mouse is you then have to take those 2D mouse positions and translate those into 3D and figure out what objects were clicked on, picked, dragged. The Three.js library has a lot of support for doing that, and Chapter 5 in the book goes into great detail about how you do a 3D pick and how you use that code to actually interact with objects. In my racing game, I didn't even use any mouse support at all. It's pure keyboard because that was a design choice for the game. And the way keyboard works is there's a standard set of key handling, but in fact it's not quite cross-browser. I've got some information in the book on that. There's some tricks to doing it so that you can get it cross-browser to get the key codes for arrow keys and those other things. Somehow, ironically, surprisingly, no one's standardized on that stuff yet. So one of the neat things about this, and I hope it's coming through on the webcast, is the car has exhaust. So we've created a particle system to do that, which is essentially an animated set of objects that have semi-transparent bitmaps to create a smoke effect. I'll run that real quick in the browser. And if you can see that, you're going to see smoky bits moving around. We basically have exhaust coming out of two pipes in the game, in the back of the car. We're going to look at that in a second. Let's quickly look at what the code might look like to do that in Three.js. This is about other than the shader, this is about as advanced as anything gets in the game that I built. And, I think any web developer should be able to handle this stuff. So let's go take a look. I've got a file called exhaust.js, which is the class for creating the exhaust fumes. And we basically create particles. We create, first, a bucket to hold geometry. That's a Three.js type that just holds a bunch of vertices that are going to be used for the particle positions. We create the basic material. It's a particle basic material. We're saying it's semi-transparent, 0.05 opacity, so mostly transparent. We're turning on a transparent flag in that material so Three.js knows it's going to do alpha blending when it renders it. We're making them 1 pixel size in drawing. And then we're going to put a texture on it, a smoke texture, which is just a PNG with a lot of transparency in it. And then we're going to generate the geometry for the particles. And we're going to give each particle some velocity as well. And we're going to put it on a little list, and then we're going to create the particle system object itself, the Three.js object that gets added to the group in the simulation that will then get rendered every frame. Now, in my update, which is basically this is the method that gets called every rendering frame, every request animation frame, that exhaust updates itself by counting up the particles. It's going to check it against some ranges in the geometry to make sure it doesn't go too high up on the screen, spill too down too far. It's basically another cheap cinematic trick to make the exhaust look like it's floating up in the air, like it has zero gravity. So this is the math to do that. It basically messes with positions using a little bit of trigonometry. And then finally we tell Three.js the vertex values in there have been messed with. They're dirty. This isn't a well-documented feature in Three.js. That's why we're using a double underscore variable to do it. So here's a place where the API could use a little improvement. We do that, and that gets re-rendered, and you see those cool particles. So last topic before we show you the full game, and this is really cool. This is kind of the secret weapon of WebGL, is how it integrates 2D and 3D. You could get other toolkits out there to build games like, so let's say Flash with its 3D stuff, and then you can try and put a user interface on top using div tags and HTML and all that. It won't work. You got to put it on the side. Or you got to make your Flash control windowless, and then you can kill the rendering performance. Or if you ever use Unity, it's a great game engine, great runtime. Besides the fact that you have to use a plugin, if you want to put any UI on top of it, you can't use HTML. You've got to go get an add-in from the Unity store, learn a custom way of doing UI widgets. You can't style it with your CSS the way you can with your regular web pages. This you can. 2D and 3D integrate seamlessly. You can create heads-up displays to layer over your 3D. You can have 3D objects with a transparent rendering background layered onto your 2D page move those objects around in a presentation. It's great for a CAD manual or something like that in a web page. You can use a canvas as a texture map, so you can use a 2D drawing program and then draw live bits on a texture. You can use video as a texture. It goes on and on. It's just amazing. So how we've used this in our game, here's a little art direction prototype that I'm also using before I put the full game together. As you notice, the speedometer controls on the bottom that are just randomly sort of moving around. These aren't wired up to the logic of the game. I'm just moving around here just now so we can explore the art in the scene. This is to just get a sense of the art. I made a little fake terrain with a flat plane and some sand textures. I'm not colliding anymore. I can go off into the distance. I brought in Route 66 signs. I got off Turbo Squid. I'm just looking at this whole thing to see how the art looks. I made a scrolling sky background with some texture tricks. And you'll notice here these 2D elements. We've got this heads-up display with speedometer controls. That was open source code I got from somebody else. I customized it with CSS, dropped it into my presentation, just worked. I've got a restart button here that lets me reload the scene, 2D UI. So finally, I know I'm running out of time here. I'm just going to run the game real quick, and then we'll come back to the final bits of our presentation. This one, I'm going to turn the sound up a little bit so you can hear. I've got sound effects. There's a sound lab in my chapter on the game development. You'll notice the head controls are now actually pegged. The RPM's pegged. The kilometers per hour are reflecting what I'm really doing. If I hit the sides, the guardrails, I screech, I bounce. And whoops, if I crash into the car, I'm going to tumble. I'm going to get that crash animation. I'm going to be invited to restart. This time I'm going to win that game. See if I can get to the finish line. Go. Did it. 21 seconds. I've done better. So there we go. Get rid of that. We didn't have time to get into a couple of topics. You should take a look at this. We're going to upload the slides too, right, Yaz? Make sure you detect for WebGL that it's running in your browser. I talked about that on the front end of the hour. You can also figure out if you've lost your graphics context. Basically, you go back and reinitialize your whole app. We put it all together into a game, and then we're up and running. We've chosen our framework of Three.js. We've learned how to draw graphics. We know how to load models into a scene now. Three.js has built-ins for JSON and Collada. We've seen how to animate and create interactions, visual effects with particles, 2D for user interface on top. We added sound. Sorry I didn't get time to actually cover that one. And we talked about how to make sure this will run cross-browser and you detect your WebGL. So with that, I wanted to, we can talk about where to go from here, but I just want to say WebGL is ready for prime time. It's running on all your browsers now, IE being the exception. We can talk about that. Strong community support. It's running on a lot of devices. The tools are a little bit young, but we're going to get there. And so I'd say for sure it's time to go forth and build. I hope this webcast and the book will help you get started on that. Here's the code. Go to github.com/tparisi/webglbook. Yaz, maybe we can share that in the group chat so people can just link on it if you can. No sweat if you can't. And then I invite you to get the book. Apparently we're running a special today at O'Reilly. Yaz, did you post that URL, or do you want to tell people about it?
Yes, thank you, Tony. Folks, if you like what you saw today, oh my gosh, and I know you do because I'm seeing the comments coming in the group chat. And like all of you, me too, I am amazed. This stuff is incredible. Tony's book is the O'Reilly Deal of the Day, and what that means is you can get it today at a really good price. Go to O'Reilly.com, look on the right-hand side. You can't miss it. It's right there. It'll save you some money today. And we did push out some codes to you all in the group chat, so we invite you to take a look at those and take advantage of it and get Tony's book. Looks like we're going to be heading towards Q&A. So, folks, at this time, if you do have a question for Tony and what he has been talking to you about and showing you, please open your group chat. If you haven't already done that, type it in, send it in, and he can answer that while he's with us.
Okay. Hey, guys, so where do I start? Okay. I see some here and I see some here, Yaz. Which one should I go for first?
Sure. If you want to take these, and then we've got this one that just came in.
Okay, great. Rodrigo Floriano asks, Tony, what about collision detection? Is it supported, covered by Three.js? There's some picking, mouse-style picking. There's a lot of math help built into Three.js. If you want to write your own collision detect, I think you need to do sophisticated stuff. I haven't seen anything advanced. Now, then again, I should actually probably disclaim that and say I haven't looked at R50 yet. I'm still, the book samples are still on R46. One of the things I have to do, these are revision numbers of Three.js. One of the things I need to do is actually go and upgrade and see what's going to break when I try and upgrade to R50. So I haven't seen what the latest is. There's also people who build add-ins for this stuff. So what I would say is go get the latest Three.js, download it, look at the samples. There's an extras directory, Rodrigo, that has a lot of stuff in it. So when I was looking at it before, it was pretty lean on collision. But maybe someone's done something. If they haven't, there's a lot of good literature on collision. There are actually some ports of physics libraries to JavaScript as well, like JGlib, which originally was coming from ActionScript, has been ported to JavaScript. Ammo, which is a port of Bullet, which was a C++ library. They ran it through a translator and mscript in, so it's hard to look at the code, but it's there, running in JavaScript. So you may need to use a physics library depending on how aggressive you want to be with your collision. Ken Penn has a question. Tony, T-Query for Three.js, do you recommend it? Sorry, I haven't used it yet. So, Ken, if you get on the bleeding edge and try it, and maybe you can let us know. Haven't used it yet. I just heard about it, though. It sounds really exciting, so that will take a lot of the repetitive tasks out of your Three.js development. David Hernandez, question. Tony, given the current state of WebGL, hardware, browser implementation, etc., when would you recommend building a game or app for the masses? That's a great question, Damon. I actually recommend building a game or app for the masses with WebGL now if you are only focused on building on a desktop browser. I know Internet Explorer is a concern, so that really depends on your audience. But yeah, I don't want to be mean, but I must say that most people I know are either running Chrome or Firefox these days. I know it's anecdotal, but I also know that Chrome has taken over as the dominant market share leading browser. So I think a lot of the consumer energy is around Chrome, and I think Internet Explorer's influence there has been waning. But that's I don't want to soft pedal it. That's still a big issue. Or if it's not for you, if you're building a game optimized for Chrome or an app optimized for Chrome or Firefox, you could be in good shape. Now, when it comes to tablets, mobile devices, etc., it may be a little tricky. What I'm recommending to people, I actually consult with companies too. They're building HTML5 games, not even WebGL, and they're finding the performance really bad, say, on an iPad. And I've been telling them to port to native, which is ironic since I'm such a champion of HTML5 and all this open stuff. But that's just the reality of HTML5 implementations today. But one of the things you can do if you have the engineering talent or you can avail yourself of a toolkit to help, there are toolkits for sort of cross-developing. So you can build an HTML5 and or WebGL app for your desktop browsers and then use a tool that kind of cross-compiles to some mix of WebKit and native code. So that's a bit complicated, but for some people who've got the wherewithal, energy, and maybe the time horizon, that might be a way to tackle that. That's the way I plan on building the games I'm going to build for myself over the next year is a hybrid approach like that. Dom May asks, what is performance like in comparison with HTML5 Canvas and SVG? I can't speak to SVG, but I can speak to HTML5 Canvas and say unequivocally that, and I think this is true on all platforms, including the small devices, WebGL is way faster. In fact, somebody recently just did a port, and I wish I could remember who it was, I just heard about it, where they took the 2D Canvas API and basically just re-implemented it in WebGL so people could take their applications they've already written for Canvas and just render them with WebGL and get a super speed up. And I've heard for sure other people taking their original Canvas games and porting them to WebGL, essentially just rewriting them and using WebGL because it renders faster. Because it's using the 3D graphics pipeline, even if it's only drawing 2D graphics, you get the benefits of a lot of hardware acceleration and you get some better visuals. So performance overall, everything I've heard anecdotally, everything I've Googled, everything I've seen up close, WebGL is far better than Canvas on all the platforms I've seen so far. Herbert Schilling asks, shadows/reflections. Three.js has both. You need to look around, take a tour of that. I actually have a sample of shadows in my book that's a fake shadow where I just duplicate the object, squish it down, and render it with a different material, but it's the same object and it's animated. It's a great, cheap cinematic trick. I had to do that because the Three.js shadow system requires a floor or some other object to cast the shadow onto, but in the thing I was doing, I didn't want a floor. I put an object on a page. I wanted the floor to be the background web page, so the shadow would cast on it, so I couldn't do it that way. But Three.js has built-in shadow support, and you can see it in the samples. They have tons. They have like 100 samples, like I said, in the demos. So there's a bunch of examples there. Reflections, I don't know if they've got any examples in the samples, but that's pretty well understood about how to do that with a shader. You can for sure do reflections in WebGL with the right kind of shaders, environment map, texture map support. You can certainly do fake reflections like a cubic environment map, and there's a lot of examples of that. Like there's a racing car demo, or a couple of them in the sample library that the cars all look like they're reflecting the background. They use a cubic environment maps for that. So between the real reflections, real time, and cubic environment maps, you're covered in WebGL. Rodrigo Floriano asks, any thoughts, news on WebGL on iOS? Is Apple enabling that? Last I knew, and my news is several months out of date right this second because I've just been paying attention to other platforms lately, is that it was built into their iAds framework, so you could build 3D ads, but it wasn't generally released into mobile Safari. And I don't believe there's been any status change on that. That's one, I'm going to go through and look at the log of these questions later and collect up the ones where I didn't have a ready answer on or a fresh one, and this is one I'm curious about. And so if I find anything out new beyond what I just said, then, I'll update with that. But I think that's still status quo. Apple hasn't moved on it. So that's one of the reasons that I am suggesting you do a hybrid approach on iOS, which is you have a library that does native OpenGL ES. It's the same OpenGL. And you don't do your drawing calls with WebGL. You use WebKit for your application. You do your drawing in OpenGL native. And with any luck, you have a tool to sort of cross-compile or do that for you so you don't have to write it twice. Okay, Dom May, question, is there a fallback mechanism if you can't use shaders? Dom, I don't know what you mean by can't use shaders. I'm going to assume you mean don't want to write the shader code, aren't technically up on shader language. If that's the case, again, Three.js has a lot of built-in support. So they've pre-built shaders for you, basically. So all of those materials I was showing you earlier, mesh basic material, mesh line material, particle basic material, mesh Phong material, those things write the shaders for you. There's another thing called the shader material in Three.js where you can kind of just give it a few parameters that it knows about, customize it a little bit, but you still don't have to write any extra code. So if that's what you meant, then Three.js has a way to do it so you never have to write any shader code. If that's not what you meant and you're still on the line, come back to me with a follow-up, please. Robin Namawag. Tony, as a beginner, what are the most common mathematics that must have to be learned to be efficient on creating a 3D application? You need some basic linear algebra. You need to know your X, Y, and Z coordinate system, your 3D Cartesian coordinate system, vector math, so how to add two vectors, because basically adding two vectors moves one vector from one place to another. The sum of two vectors is the sum of its X, Y, Z components. It's that simple if you remember that stuff from math. Transform matrices, so a basic 4x4 matrix. Those are used to move vectors and other objects around on the screen. If you have those, you ought to be good to go. You don't need anything more than that to do basics. And even the matrices, the good thing about a toolkit like Three.js is you don't really touch the matrices that often. What you do is you set the position, orientation, and scale, or position rotation, and scale properties of your Three.js object. Under the covers of the Three.js library is copying those into a matrix for you. So if you can think in, okay, I want this position to be 5, 2, 1, that puts this vertex in a certain place. I want the orientation to be around the y-axis. It's basically axis angle, so I want a 20-degree around the y-axis. Oh, degrees are done in radians. Those are, they're not degrees. Angles are done in radians, not degrees. So you got to look up radians. So that would be the one other thing. You do all that, and you can build what I built in the solar system. And trust me, one of my deep, dark secrets, which I'm letting out to the world now, is I don't love 3D math. I hate doing it. So that's why I like using a language like a library like Three.js. So you should be good with those. Last question. Jared Simpson asks, could you address some of Microsoft's reasons for not supporting WebGL for IE? I don't know what to say. It seems political.
and any answer you'll get from them will probably be political. They have their own technology called Silverlight, and they are continuing to push that. Originally, it was sort of a competitor to Flash, and now it's got some 3D in it, the way Flash has some 3D in it. And beyond that, I can't see why. There's been talk about security issues in the browsers, but as it's been determined, all of the security issues that WebGL has around shaders possibly compromising hardware, blue screening your machine, those exact things happen in Silverlight and Flash 3D as well, and Unity, and any other 3D engine that gets to the graphics card. So, Microsoft's concerns might as well be pointed at all of interactive 3D graphics. So, those are the only ones they've claimed to be legitimate concerns, and even those I think are slightly political. So, I hope someday they change their minds about that, and I believe the way that's going to happen most forcefully with Microsoft is they listen to developers. So if developers are building really cool things in WebGL, and you see a lot of WebGL killer apps out there, then I think we're going to see Microsoft change its position on that sometime soon.
Alrighty, folks, that is all the time we have for questions today. We do thank you all for sending them in, and with that, we're going to say a really big thank you to Tony for presenting a fabulous and outstanding webcast. We thank all of you for attending and hope you benefited from today's webcast. We'd also like to remind you, Tony's book is the deal of the day. Oh my gosh, folks, all the things he showed you today, and there's so much more in the book. We urge you and recommend that you go to O'Reilly.com, look on the right-hand side. You can't miss it. It's right there. Again, we thank you, Tony. We thank you, everybody, for attending. This will conclude the webcast. Goodbye, everyone.